Yesterday, what I made the mistake was when I was writing the quantum numbers of gain for the W, I think I wrote 131. It should be 130. It was majorly confusing. Okay, I'm sorry. I think it should be 130. Okay. Yeah. Any questions on yesterday's part? Or Tuesday's part? So, up to this level, the main important thing, conceptually, what standard model introduced in a gauge symmetry in a renormalizable way is the concept of approximate symmetries. The main jump compared to the three theories, no, we said standard model has three theories. The weak interaction theory, which is essentially the V minus A theory, okay? Strong interaction theory, weak interaction theory, and then electromagnetic theory. And these two combine in the standard model to form electronic theory. Okay. Now, compared to in strong interactions at low energies, there is this concept of approximate symmetries. Okay, so there is the concept of approximate symmetries. At high energies, the symmetry is exact. Okay, at low energies, there is this concept of approximate symmetry, which is given by the name of chiral symmetries. The chiral perturbation theory works on the idea of approximate symmetries. Okay, so there is at low energies. Anyway, this barrier again I said is given by something called lambda QCD, right? High energies, exact symmetry. Approximate symmetry. Now, weak interactions also wants to work on a single lines, but it's built. The energy scale is very high. In this case, I should be very careful when I say energy. Here it means more like temperature. At high temperatures, you can restore the entire weak interaction. Okay, at high temperatures, high densities and everything, you restore the entire weak interaction. But it's spontaneously broken. So, weak interaction is an approximate symmetry, pretty good approximate symmetry at lower energies, but this scale is around 100 G. Again, good symmetry. Let me not say it's a complete symmetry, okay, because it's a good symmetry at high temperatures. This is a questionable thing. Okay, we'll come to it maybe in the next class a little bit more. Weak interactions can restore the symmetry. Even weak interaction symmetry is completely restored, meaning in the sense you have full isospin symmetry at high temperatures. The temperatures around 100 GeV or more, you restore symmetry. I'll come back to it when I'll talk about maybe today it's a better one. Okay. Whereas electromagnetic theory is exact all through. In fact, QCD is also exact all through. The symmetry, which is an approximate symmetry, which is explained, is not the same symmetry as SU3C. This is always conserved. SU3C is always conserved, whereas this approximate symmetries which we use to apply, these are something called chiral symmetries. These are different symmetries. It's a completely different set of symmetries. It's a global symmetry. Okay. it's like a bird's eye view of that. Okay. Yeah, but anyway, we only need the bird's eye view as of now because it's a full semester will take course actually. Yeah. So these symmetries are different. So the point I want to make was that weak interactions are sort of special that they even these theories are not completely accurate theories in the sense they are non-renunciable, these are effective theories. Whereas weak interaction theory or the Weinberg-Salam model is the only theory in which approximate symmetries are very well established in a renormalizable way. Okay? They are not global symmetries, they are local symmetries. Okay? They have very nice quantum physical properties. They give you soft breaking terms. There are no hard breaking terms. Okay? This is the only thing in which you can understand weak interaction in a full quantum physical point of view. Accurately, you can understand it. Okay? Weak interactions, the approximate symmetry point very well. So why it is an approximate symmetry? You can mathematically put it very nicely. This approximate symmetry in a fully quantum physical point. Compared to say chiral symmetries or linear
symmetries. Because it is broken.
It's broken.
For that reason,
yeah, and it's not broken at the quantum level. Today I'll talk about the quantum level actually. So it is not broken at the quantum level. It's broken at the classical level. So at the quantum level, the symmetry is exact. Okay, weak interactions. So at the lowest energy state, if you want, so this is spontaneous symmetry breaking. So you have some sort of a double well potential, and the lowest energy, you believe that the universe resides in the lowest energy state. And at the lowest energy state, the Higgs obtains a vacuum expectation value. Vacuum expectation value means that the field value is non-zero, meaning at the lowest energy state, the field value is non-zero. That means it's only possible for a scalar field, in the sense that we have non-zero probability of finding a bunch of particles at the lowest energy state. And you are now building your quantum field theory around it. So if you want to put a bunch of particles, you can only put scalars because they cannot reside in one state. You cannot have fermions in one particular energy state. They violate Fermi, Pauli principle and so on and so on. Or also, in other words, they also violate Lorentz symmetry. Okay, we have fermions in the lowest, in the single state, they also violate Lorentz symmetry. But we are building quantum field theory, it means Lorentz invariance is infinite. Now, at the quantum level, meaning when you write the quantum theory, okay, around this zero state, meaning around the vacuum expectation value of Higgs, this theory completely satisfies the Lorentz symmetry. It doesn't violate. All the violation of the symmetry is coming proportional to the vacuum expectation value. In the limit, vacuum expectation value goes to zero. It's a dimension filter. Okay, it's not a dimension higher dimension term. It's a dimension full term. The vacuum expectation. It's like a mass term. So anything which comes as a mass term, you can set. These have nice Reynolds group properties. These are called soft terms because, these are also called super Reynolds group terms. Okay, so in the limit, this term goes to zero. Meaning, if you set the mass to be zero, this constant to zero, you have full restoration. Okay, any violation of the symmetry is proportional to the small constant term. Okay, either in the masses of the W bosons, okay, or in the masses of the fermions. Anyway, this is always proportional to one particular constant in the theory, which is the vacuum expectation value. Okay, so if you break symmetry by some dimensional full terms like soft, it's called soft breaking. So spontaneous symmetry breaking is a soft breaking of the theory. It only gives you two mass terms. It won't give you new interactions. It won't give you dimensionless couplings. Okay, breaking of the symmetry only by dimensional field like mass terms is called soft breaking, And spontaneous symmetry breaking always leads to soft breaking of any symmetry. Now you can break electroweak symmetry by adding some dimension 4 terms. Those are not generated by spontaneous symmetry. You can imagine that I can write any term in the Lagrangian which can break this. But none of those terms are generated by spontaneous symmetry. Okay, so suppose if I write a term like QHH, this makes electroweak symmetry breaking. But this is not allowed by the gauge symmetry also. Okay, and also anything, any term, dimensionful term, say for example, take psi bar, doublet, say for example, L dot H dot H. Okay, so anything or y q dot q. This term is not generated by spontaneous symmetry. This is that okay? This is higher dimensional term. Okay, none of the terms which give you this term can say, for example, lead to proton decay. Okay, so if you want a more exact term, would be L dot Q, something like that. You can write all kind of terms which can violate the symmetry by dimensionful terms, meaning you are adding higher dimension or any coupling, new coupling or something. Okay, something like just take the analogy with Fermi theory. Fermi theory is a current interaction, essentially. Okay, so it has terms like n bar b minus a. So I'll just write b minus a. These are currents. P bar b minus a. U. This is just the Fermi theory. That's it. Simply you have one current neutron proton, one current electron, and this is a dimension something Fermi constant times it is df. This term is generated. Okay, this term is generated at the effective level in the standard. It's generated by the effective level because when you resolve it, it comes proportional to the masses of the W bosons. Okay, so this term is non-reducible in the Fermi theory, but this is resolved. So this term again is dimensionful. Okay, what I mean say, dimension 4. This is dimension 4. When you resolve it, so even non-renormable terms are converted into renormable terms, into dimension 4 terms. Higher dimensional terms are converted into dimension 4. Also, this is one thing because you are going into short distance system. Other thing is that all the symmetry breaking terms are dimensional. All the symmetry breaking terms are dimensional. That means any term will be proportional, which breaks the atomic symmetry breaking, will be proportional to B. A dimension full in the sense that they have couplings which are mass dimensions. Either they are mass square or mass. So this will give you mass squares for gauge bosons, mass for the fermions. So such terms are they are called super renormable terms. So it only leads to super renormable terms. So spontaneous symmetry breaking always leads to soft breaking of any symmetry. There is something called hard breaking of symmetry. If we have introduced new interactions which violate the symmetry, which are dimension 4 like couplings. Dimension 4 like couplings. Okay. Dimension 4 like couplings are you introduce a new power interaction, but which violates say the symmetry, gauge symmetry. It can be simply done by say if we have a new power interaction which is not determined by the Higgs-like interaction, but which comes from a term which is not like for example, take a term like LES. S is some singlet. Okay, this leads to a new interaction where instead of the Higgs you have some other scalar. This will break the symmetry. Okay? This is valid. This is not generated by. Okay? You can break the symmetry by any term, any arbitrary term you want. But spontaneous symmetry breaking has this nice feature that it really gives you full dimension. Now, yeah, okay. This is important feature of standard model. And for any physics beyond standard model, there are 2-3 directions we'll tell you. I'll come back to it a bit later. Yeah, I hope this addresses that. Any questions on spontaneous symmetry breaking is equal to soft? Okay. So, now, okay, the other thing mistake I made the other day was when I was talking about gauge symmetries. I think I wrote the term as 1 by G W mu W mu. One of them should be theta mu. This delta W is equal to delta del mu theta. I think I wrote W mu W mu. I think it should be theta mu W mu. Then it brings the FABC. Because thetas and W's transform the same manner because they are in edged representation. Yeah, I know many of you have not taken the standard model course, okay, but I'll try my best not to worry too much about the standard model lecture because we'll swiftly move to beyond standard model. I'll only capture the essential points of the standard model which are required for me. Okay? But it is better that you go back and look at the standard model, and I will share with you one OneDrive folder with all possible references, latest references, whatever you want, in various sections. Okay. So we have seen the classical symmetries. There are several bunch of symmetries we have seen, which is the standard model features. Why I am listing all these features, you will understand it once we start constructing some BSc models. So let me just believe that there are two gods called Weltman and Prof, because I won't go through the details. And they showed, these two gods showed us that the standard model is renounced. Okay, let's say that standard model is a renounceable. Actually, what they showed is much more generic statement. They showed that spontaneously broken one of the non-linear abelian quantum theories renounced. Now, I won't go into the details of what renounceability means, but at the practical level, what it means that I can compute higher order corrections. This theory is complete. So, what does renounceability mean? Renounceability means a theory is built up of some n parameters, and if you compute higher order corrections, and these higher order corrections typically have infinities in them, the number of parameters are sufficient to absorb the number of infinities you generate. So you can always renormalize your parameters, parameters such that your theory can be physical without all these infinities. Okay. So if a theory has n parameters, say for example, the number of kind of infinities you can generate should not be more than n times. Okay? So you generate any order by order. In perturbation. See, the process of renormalization is two-step process. In the first step, what do? You regularize the integrals. Okay, you regularize the integrals. I'll come to what these integrals are in a second. And then, plus isolate them. So you isolate the infinity. And then in the process of renormalization, you observe the infinity. Such that, say, and define physical quantities, say G physical is equal to, or G physical or G renormalized, sometimes it's called G renormalized. G renormalized, sometimes it's called is equal to, I'm just talking technically, identity renormalization. This is called the bare coupling, and this is the infinite part. Plus there are finite terms. So you observe these two, and the physical thing is proportional to some finite terms. Now, where do these infinities come from? So let's take a simple example of 5-4 theory, Ikawa theory. Okay, let's take a simple example of the 5-4 theory. Also happens Ikawa theory also. So now maybe let's take a Ikawa theory that's more. Let's also add a Ikawa term. Any theory. Let's take QD or whatever. Which theory are you comfortable with? QD or something. Okay. Any theory, quantum theory, in which let's just write down the vertices. No, it's easier. So there's a vertex like this. Okay, this is a photon and a vector. Let's just take the example of QD. It's better than this is something which you all study and so on. So F. Okay. QD is a very simple theory. It has only one vertex. It's a very nice theory. You can calculate at all orders, except that if you have the energy to calculate. Okay. It may take 50 years to calculate a 4-2, but yeah. So it's a very nice theory with only one vertex, unlike standard model which has thousands of vertices. Okay. Now you can write higher order process. The Lagrangian is very simple. So del slash minus m psi bar psi minus f mu. That's it. This is the entire Lagrangian of QD. Very nice. Okay. And it has only one vertex in terms of Feynman diagrams. So now you can compute various things. So a photon propagator is there and a fermion propagator is there. The photon propagator will get corrections of this type. The fermion propagator will get corrections of this type. On the order. Now if you try to compute this loop, okay, let's try to compute this loop at some momenta. Okay, let's just say T K T minus K So if I try to compute this loop for the photon propagator, this has an integral which goes as e plus k plus some numerator is there. Okay? Let's forget about the numerator. Okay. Now this should be k. Sorry. Now k is completely unprotected by the external momenta, so it should be integrated from L. It is completely unprotected. For small p, you can forget the external momenta. External momenta is p, we can forget about it. This goes as d power 4k equal k square. So if you convert d power 4k into dk square k square, you see that this is quadratically divergent. So that we get large.
P plus k times k.
Right. P minus k. Which one you are talking about?
P plus k times k.
Which one? P plus k
And k square.
Okay. So this is logarithm being there.
This is Fermi property.
No, this is quadratically divergent.
No, this is Fermi property. So this should be the
Yeah. This is at the end of the day, this just goes as k square. Yeah. See, on the numerator there is also k square. Okay. Here. So this goes as this is numerator is p plus k plus mf. Okay. You can neglect p and k and everything. So there is a k square on one equals. Okay. So roughly it goes as this is quadratically divergent. If you want, there is a k square on the numerator. Okay, let's put it this should this. I'll say okay. I don't have this has an infinity at large momenta. And the limit k tends to infinity. This entire thing goes to this amplitude goes to infinity. This cannot be a physical infinity because there is no physical cutoff or something. Okay? This cannot be a physical infinity. So this is a artifact of the way we write our Lagrangians, and it's an artifact of perturbation theory. It's an artifact of. I give you. There is a book called Renormalization by Collins. Actually, you should read it. It's a very nice book, and it tells you what are all the reasons why you need renormalization. Or you can also look at. I personally like the old Bjorken and Drell's book or Schweber's book on quantum theory, volume 1. He writes it in terms of wave functions and connects it to the quantum mechanics. And what do you get? Because we are not using. The reason is we are using. There are many reasons. One is this quantum interaction. Then it's a quantum interaction. The other is that we are using free particle solution wave functions here instead of actually the interacting wave functions. What we call as interacting wave functions are essentially nothing but free particle wave functions. At the end of the day, in your perturbation theory, we are not using the full wave functions. So there are a number of reasons, but anyway, in the way we compute, there are infinities. Okay, and these are not physical, and we want to get rid of them. Okay, we want to get rid of them, and so we use different procedures to regularize the infinity in this amplitude. And the two most famous ones. So now, here was the question of at the quantum level what happens when you are trying to regularize the integral. In QED, I'll still example in QED. In QED, there are only two regularizations which satisfy the gate symmetry at one loop level, at iron loops at the quantum level. And how do you know that there is, at the classical level, the symmetry is conserved by checking something called the Noether current, right? There is a Noether current associated at the classical level. At the quantum level, there are Ward identities, Ward-Takahashi identities, which tell you the symmetry is conserved. Okay? So there is Ward-Takahashi identities. this tell you the symmetry is conserved. So the regularization which we choose should be such that the Watt Takahashi identity should not be satisfied, should be still satisfied. Okay, they should not be, if you use a cutoff, something like that, massive cutoff or something, it violates the gauge symmetry at higher order. Okay, so you have to be very careful what regularization you use. So one of the most important, there are two things, but one is lattice people use. Okay, we don't care about it because as of now we don't care about it. At some point maybe we do, but as of now we use something called dimensional regularization, which conserves the gauge symmetry at quantum level. At the quantum level, the gauge symmetry conservation is incorporated in this Watt Takahashi identities, and you use a regularization scheme which is called dimensional regularization. Isolate the infinity. You isolate the infinity.
What is the meaning of quantum symmetry?
Huh?
What is the meaning of quantum symmetry?
Quantum symmetry in the sense that the Watt Takahashi identities are something like this. That if you take a given process, say for example, okay, if you take a given process, some amplitude m, say for example, with some photons or something, they tell you that a mu and a mu should go this way. This is the coordinate that we can take the external momentum and match it with the the amplitude. Okay, so at the quantum level also, that means at the loop level and the diagrammatic level, the gauge symmetry should always be conserved. Now, why it is not manifest? Why do you need symmetry? Identities is because gauge symmetry is not an exact symmetry. It's not a proper symmetry. You can always choose a gauge. When you quantize the electromagnetic field, you choose a gauge to quantize it. Okay. So it is not manifest that the gauge symmetry is always conserved. Okay. Some of these gauges are not manifest that the gauge symmetry is conserved. So you choose a Lorentz gauge, you choose a Coulomb gauge, you choose some all kinds of covariant gauges. Whether you choose a non-covariant gauge, it's a bigger problem. Okay, whether you choose a Lorentz gauge, it's a covariant gauge. Okay? But if you use a Coulomb gauge or something which is a non-covariant gauge, that means it's not obvious in a quantum physics setting. So you do the best way is to use something called RZ gauges, which are in quantum. Okay? So you need to make sure this is a statement that the symmetry is conserved at the quantum level. That means any process you compute at one loop level will satisfy the gauge symmetry. So the Lagrangian is an artifact. The physical thing is a process, right? Okay, Lagrangian is just an artifact. It is just an operator, bunch of operators. You can add some terms to it or something. But the physical thing is a bunch of process. This process should satisfy the symmetry. So that is manifest in this kind of identities, which is called the Watt Takahashi.
I mean, so this condition will ensure that no matter what the gauge I choose, the physical answers will be the same.
No matter what gauge you choose, the physical answer will be the same. Yes, exactly. Exactly. Yeah. Though it may be hard to see it, okay? In some cases, it's always the same. Yeah. Whatever gauge you choose to actually calculate things, you'll end up having the same answer. That is correct. Okay. So now, in the QD level, there is something called so you can show it order by order renormability, but there is a mathematical technique to show that the theory is completely renormable at all orders. Okay, it's a very, very complicated thing. Okay, I won't go through it. It is some scheme. If you want, you can look at it's called VPHZ theorems. Okay, you can look at the easiest book to look at is essentially Bjerkman and Volume 2. Okay, there are other books also which do it, but there is something called Weinberg theorem which does one another. There is something called Forest formula and everything which he works on. He works on even more complicated things like topology and stuff like that. But there are this there is this scheme, essentially which works very well. Okay? Which tells you that QED is renormable at all orders. So you can compute it at any order in perturbation theory. You'll get a finite answer. You can always renormalize it. You get a finite answer. Now, the same thing can be applied to standard model. Same thing can be applied to standard model, except that in QED the symmetry is always conserved. Okay, but in standard model it looks like it is not conserved because you have symmetry breaking center. But at the quantum level, it's always conserved. Okay, so very analogous to these equations. The equations of Slavnon-Tyler are completely slightly involved. I won't write to them, but I wanted to write the full quantum Lagrange one, but the last time I wrote it, I lost a lot of people. They were not listening. It was so technical. Okay. So, I will do that, but anyway, let's do that. Okay. I'll just scheme out because QED is much easier to understand, so there's the reason we can write it on. Okay. If you want, I recommend 2 lecture notes. Holic, they are there with me if you want, and then take a later. I'll put them in the Prof box. One right. These are called renormalization of standard model. Renormalization of standard model is actually this is the summary. It is in early 90s actually. So proofs that come actually renormalization of the standard model in a way started even before the standard model was constructed actually. Okay, it started in 1950s. So people started computing one-loop corrections to muon decay. Okay, muon decay was known in Fermi theory. So Sirlin and company found it. Sirlin and the person most famous person in G-master calculations. Who did the for loop QD for the G-master? No. Okay, this is a homework problem. You guys have to find out. Okay, he is the co-author who died for loop contribution to neon G-master can easily be applied to as well. He's a Japanese settled in Cornell. Okay, that's all he said. Okay, he and Sirlin did in the 1950s when they started computing muon decay one-loop corrections. But this is a non-renormable theory, so they found out corrections to delta GF. They were doing to delta GF. GF is essentially 1 by V square. V is the back expectation value of the standard. In the Fermi theory, and then after the result, people were Sirlin and company started doing in the late 80s denormalization of the standard. This time instead of the Fermi theory, it's essentially the full standard model. They started doing it. Now everybody has to choose a scheme of renormalization. So I told you the renormalization involves that there are what are the finite terms you leave and what are the infinity. When you observe the infinity, you have a choice how you observe the infinity. Okay, And this choice is called scheme dependence of the denominator. So every quantity, every physical quantity is renormalization scheme dependent in a quantum quantity. Every physical quantity. Okay? Every physical quantity is a renormalization scheme dependent. There is nothing called renormalization independent quantity. Scheme independent quantity. Everything, if you tell what is the mass of an electron, you have to actually tell what is the scheme you are asking for. If you are accurate, actually, okay? If you are accurate, you should tell what is the scheme. In MS bar scheme, this is the number for the electron number. Okay? Every quantity, physical quantity is renormalization scheme. So the 8 is the renormalization of the standard model was done, and they use something called the on-shell scheme. So standard model renormalization was done in the on-shell scheme first. So what does the on-shell scheme do? On-shell scheme keeps the masses of the particle exactly at themselves. The renormalization scale is chosen, okay, to be the mass of the particle itself. Say for example, if mu is measured, renormalized at certain scale, you renormalize it at the mass of the mu itself. The renormalization of the scale. So the mass of the particle is on shell. On shell means if you write down its propagator, the pole of the propagator is mass. In this renormalization scheme, if you write down the quantum field theory in this renormalization scheme, the pole of the propagator is exactly equivalent to the mass of the particle. Okay? Okay. Later on, the renormalization scheme, so it was started in the late 80s and everything. The main point why they want to do was, by the time all the three-level Lagrangian has been sort of understood, okay, or the standard model. So people found the charm particle, people found what do you call it, bottom mass, everything was found by 80s, charm, bottom, everything was discovered except for the top. Top was discovered in 1995. Okay? So everything was discovered. So the three-level Lagrangian was known. But then in the 90s, there was a new collider that started. So this collider is called LEP. And this collider essentially drove full one-loop renormalization of standard. So this is a very high precision. It was essentially trying to discover things actually. Okay, it's a very high precision collider. Okay, it's an E plus E minor collider, so it's very precise. So you don't have much background. You can actually study the standard model at a very nice things. It started with an interest of what 180 or something around the Z2. Okay, it wanted. By the time W and Z boson particles have been discovered in some hadron machines. Okay, so this collider had some interest, which was then later increased. Around Z mass. What is the mass of the Z? 91 G. But then this 2 came out as a result of the experiment. Okay? This precise measurement came out from the result of the experiment. This 2 came out. Okay, so people started doing renormalization of the standard model in the 1980s and early 90s. When the experiment
This pole of the propagator being the mass of the particle, isn't this something which is, scheme independent? Because propagator is something which...
No, if only in this scheme that valid is completely valid. Propagator can also be the gauge dependent.
Okay.
I mean, so if you write a propagator in RZ gauge, there will be a factor xi.
Okay.
Okay.
Okay, yeah. For scalar fields, I think.
So it can be gauge dependent. So you need something. That is the reason why this scheme is very nice. That you can actually, like, if you want to define mass properly in quantum theory, you can say it as the pole of the propagator. That's what we study in quantum theory. And this scheme makes sure that definition holds true. But that's a scheme dependent statement. It's a pole of the propagator process. So this started. So then the renovation of the standard model was done completely in another scheme also, which is called MS bar scheme. You can study these two schemes. It is called Birman subtraction scheme by this scheme, because you are measuring not only the, you started measuring all kinds of variables, okay, at the z point. So it was better. So while this option scheme was good for masses, for couplings and other things, it is better that you use MS bar scheme. So that was the reason. Now everything is in MS bar. You can convert from one scheme to another by some formulas. So some calculations are done in MS bar scheme, and some formulas are done in non-shell. You can convert from one to another by adding. Typically, these renormalization effects, if you move from one scheme to another, those effects are called threshold corrections.
So, is there any preferred scheme or conventional scheme?
Now it is the preferred scheme is MS bar scheme. Just take it as MS bar scheme for all practical purposes. And here for the regularization.
Is also best for tire divergence.
Pardon?
The also scale is best for tire divergence.
Pardon? I don't understand.
For tire divergences, like
That's the problem actually. If you want to complete two loop, then it becomes complicated. So this was all fine because even now the full two loop renormalization of the standard model is not done. Standard model is only renormalized at one loop. Even though Tooth and company have shown that it is renormalized at all of it, renormalization of the standard model at two loop is complicated because of different mass scales are there. So another students are working on various diagrams and everything. Okay, how to calculate the two loop diagrams and stuff like that. Okay, so this is highly complicated. It has many implications. We have not completed the full two loop renormalization of the standard model. The only thing which has been completed is only the electromagnetic charge. Electromagnetic charge has been completed at two loop. So alpha EM is done at two loop. But many things, like for example, are only partly two loop, some estimates of two loops and something like that. Okay, but nobody has done the full two loop of the standard model, all the couplings, say, for example, everything at two loops is not done. Okay, parts of it are done. The infinite parts are done, not full the finite parts. Okay, so
Can
now
you
that I
explain
understand,
what is jet pole?
pardon?
Can you explain what is jet pole?
I'll come to it. First, let me write down the Lagrangian, and then I'll come each part of the Lagrangian. I'll start with the gauge part only, so I'll come to Z pole right now. Okay, so L classical, again as I said, I'll always, at the quantum level, L classical is sufficient. Okay? I won't write the full quantum Lagrangian because in the gauge fixing terms, the ghost fields and everything, it's a large Lagrangian. So if people wear t-shirts with standard model Lagrangian, it is not correct t-shirt. Okay, it's not correct Lagrangian, it's a classical Lagrangian. It's not the quantum Lagrangian. Okay. Okay, it's not an equation of my universe as written on my t-shirt. No, that's not the correct. Okay, yeah, L classical is good. Fermion. What did I start with? Fermion and Picava. So it is true at the classical level, at the quantum level. So if you want to write the one-loop effective Lagrangian of this theory, this term talks to this term plus this term plus this term. This term talks to this term plus this term plus this term. So everything gets completely mixed. You cannot have different sectors. Typical, because it's a perturbation theory, the three-level Lagrangian works rather well because it works most of the time. Okay, and the corrections are very very small. Okay, but they are not very very small. So you want to compute these corrections so that you can match with experiment. So whether you can actually do this renormalization and match with experiment, and whether this is valid in the quantum theory at the quantum level was the question which was asked by the left experiment. Okay. So you write down all these theories, you know that this is valid at higher order, but it's only theoretical. Okay. You want to check it experimentally whether whatever we have computed theoretically is valid at experimental level. So for that, you need an experimental precision which can compute at very high precision all the physical parameters, and then you need also theory which computes at higher order, and then you can match with each other. Now the problem what happens is that when you renormalize like this parameter is going to this parameter is going to this parameter is going to this. So you have to choose always a set of parameters, okay, as a starting parameters. How many parameters you choose? Okay. So the renormalization and fitting this entire thing, especially related to the gauge sector, goes under the name electroweak precision test. So today we will at least look at this part. So electroweak precision test dominantly look at the gauge sector. Okay. Okay. So what do they contain? They contain the gauge particles. Okay. So you have connections to W bosons, corrections to the Z boson, corrections to the photon. See, these are also valid. Okay. So I wrote down only 4 diagrams, but you can also have diagrams which involve other gauge bosons. Okay. So I will wrote the fermion contribution. Okay, we'll come to why I chose fermion contribution, because I am biased towards BSc physics. Okay. Otherwise, you had to write down all possible diagrams. Okay. So now, if you have an E plus E minus collider, say for example, it gives out E plus E minus, they annihilate. It annihilates to do the process, either through a gamma, and then it produces FR bar, and then it also can produce a Z. Okay. Now the couplings are here. Now, if you choose your initial E energy, so this is something called an external process. So that means in external, the momenta of these two just add up. Okay. So if you choose your external in such a way that it sits at the pole of the propagator of the Z boson, so you will start producing millions of Z's. Okay, that's called Z. Okay. So if I choose my S to be equivalent to MZ square, okay, then you can measure very precisely. You have millions of Z's produced, and all of them will decay to FFR. Most of them dominantly decay. You know what they decay to, because they decay to all the fermions. There is some universal. So you can choose whether the hadronic decay channels. You can each precise channel you can measure. Okay, Z going to FFR, meaning F going to BB bar, Z going to BB bar, and Z going to PT bar. Not PT bar, sorry. PT bar, Z going to BB, EE, everything you can measure precisely. Every partial width of Z can be measured at higher one level. Measured at one level, at high, whatever precision level essentially. Okay, and then you can also measure the mass of the Z by kinematics very precisely. So you know what is mz very precisely. You know, okay, and then gamma Z for various channels. Okay. Gamma Z means the lifetime of Z, okay, or the width of Z, okay, Z width for various channels, like for example BB bar and so on. One of the most interesting channel is the invisible channel, which is going to Newton. Z going to minimal. It's also called gamma Z invisible. Now when you measure this, now you measure this and then you fit it with the theory. Because you have the one room normalized theory, you fit it with the theory and then do the full analysis. Nowadays the question analysis is so advanced that we have several several observables. A bunch of observables are there. Not just the partial bits of Z and this thing. You also have sin square theta W. You have alpha N. You have alpha S. There is actually not alpha S, but there is some parameter associated with alpha S. Sin square theta W is a weak mixing model. Okay, this is also one more as an observable. Then there is GF. Then you have all these processes, various processes, neutrino stacking, electron stacking, and number of stacking processes. So you do, I'm not giving, so what you do is, because MZ also MW is. So when you are renormalizing, I said all these parameters are mixed up. All these parameters, everything appears both on the left hand side as right hand side. And then you also have nowadays n peaks. And then of course the most dominant one is n tau. So what you do, and then you have a bunch of observables which are called RB, RC, tau, RE, R mu, n number of these are all the partial bits of this, right? Then there are other bunch of products. Now you combine, when you do a global analysis, you don't just take the collider data, you take data from atomic parity variation, you take data from neutrino scattering experiments, you take data from what do you call Barber, Bell, and other things, low energy experiments. So you combine low energy experimental data as well as collider data, and then do a full global analysis of how the standard model fits at the quantum level. Okay, to these all these observables, to these observables actually. Typically, in most of these electronic equation tests, we choose some 5 observables, MW or MZ, one of these things, MD, and MD is now very well precise. Then there is some parameter called alpha S, phi or something, hadronic. This is slightly technical, I won't go into this. This is a term which appears in the determination of alpha S at a renormalization level, which is determined, which is essentially trying to determine from hadronic channels alpha S. Let me call it as alpha S for practical alpha S as hadronic GF alpha U. You choose this as your input parameters because these are very well measured, and if MT is not well measured, you don't care about it. Okay, you take science which is very well measured. There are some discrepancies. There are some discrepancies. So these 4, 1, 2, 3, 4, 5 parameters will overfit actually. Overfit some 20 odd observables of the electronic position. 20 plus observables of electronic position. I can show you the list next time. Actually, the transparencies, if I want to show that, I can project it there. I can try to project the list. There are tables. And now what you have is that with just this 1, 2, 3, 4, 5 parameters, as is your inputs. Okay? These are all high precise measurements. You fit the data. And the standard model fits very, very, very well. In fact, both fits very, very well. And there are something called the pull diagrams showing if there is some discrepancy from the data. So how well the theory does. So you use this compute theory and then match it with that. You use this input parameters in all your theory calculations, and then you get list of observables in theory. Then you have this list of observables from the experiment. You match how well they match, and they match very, very well.
How these parameters are related to the parameters we have in the Lagrangian?
MZ is a parameter in the Lagrangian. It is related to g square plus g prime square by 4 b square. Okay, MZ square is equal to this. Is the formula. G prime. Our sin square theta w is g prime by square root of g square plus g prime square. Okay, this is sin theta w. Alpha is synchronic. Okay, forget about it. Okay, GF is again B proportional to G. I wrote to you 1 by 2 into 2. Well, okay, alpha M is a parameter. Essentially, is nothing but it's what sin square theta W G square. Okay. Now it will be the opposite.
So these relations are valid in all.
So you can use it. These parameters are sufficient to compute all these 20 odd. These observables are like E plus E1 is going to some BB bar, say for example. Okay, or tau bar. So this will involve some. There is actually very, very one important observable which I will talk something called forward backward symmetry. I didn't go into the details, but there is something called very important observable called forward backward, which measures actually the sin square theta. Okay. So because it's a parity validating process, you want to check the forward backward. Forward term, even though the exponent is forced by symmetry, the forward should not be the same as backward because parity validating. Because only when the spin projection is in the opposite direction, you can have the cubic interactions. So the forward and the backward number of events would be different. So that will give you one more observable, and it can be computed in the theory. Okay. So these are a bunch of observables, like for example, E plus E minus this thing, then forward backward asymmetry, and so on. So we measure all of these things. Okay. Are you satisfied?
I'm just confused. So in the Lagrangian, I have some parameters.
Yeah.
So when I'm
These are all related to Lagrangian. These are all Lagrangian parameters in real sense. So this will be proportional to the value of the particle. I just wrote it as real. So some bunch of Lagrangian parameters which I know very well, I take them as inputs. And rest of all the processes are computed
these are renormalized or
These are renormalized. These are renormalized. I take them as inputs. But the rest of the things like MW mass, I'm computing it from this. I'm taking MZ as input. I'm computing MW mass as output. Okay. I'm taking Sanskrit W as input. And using that, I'm computing MW mass at high level. And now I'm matching with MW measure nodes. I match it with the MW measure nodes.
So these are the parameters I'm starting out with at some scale.
You choose some 5-6 parameters typically. The choice, there is some, now there is a redundancy in choice of parameters. Actually, now the data is so good that you can choose some other bunch of parameters. Not exactly this choice I made. So you can interchange MW with MZ, okay, so on. So the only thing which is not fit is essentially the top mass. So it is still highest uncertainty comes from two things. Earlier it was coming from two things. One is called top mass and one is the Higgs mass, but Higgs is now we know very well. So the main uncertainty in relative distribution test comes only from the top mass side. Okay. Top mass is very good. So what it tells you is that standard model at the gauge level works very well. Okay. So this process, how are the crystals coming in? Because these loops are here. The loops come in this process. So you computed one loop and the formulas go in. And top also goes in. So you are measuring this process actually as a correct with the loops and everything. Okay, any questions on this? So, yeah. So, for as a takeaway, remember that what we remember as a takeaway is that these diagrams, these 4 diagrams, are very, very important. Okay, with WW, gamma gamma, ZZ, and gamma Z. Gamma Z, there is no tree-level interaction. It only happens at one level. Okay. So these 4 diagrams are very, very important, and later on this will play a very big role in BS integers. These 4 parameters, we'll call them as some pi's. Pi's are self-energy. Okay. So pi. W. So this is some self-energy. These 4 self-energies are very, very important. These we will call them as the STU parameters. The combinations of these 4 diagrams are the STU parameters which we use here. So if somebody asks me what is STU, for every BSM model, it has become a norm to say what is the STU parameter for this. So these STU parameters are nothing but linear combinations of these 4 diagrams. Okay, in the new physics model, if there is a physics, it will modify the gauge sector. But the gauge sector is so well measured at per percent level. Okay, at the quantum level also, you know the new physics cannot enter. Okay.
So from the left experiment itself, what's the Higgs mass spectrum was created? I mean, it was mostly, as you mentioned, the MG was the highest function. So
Yeah.
MG and Higgs can correlate from the diagram side. So
Yeah, actually that's a nice story. Actually, it's very good point you raised. If you take now this is, if you want, you can find as a puzzle. If you take MH and MP as free parameters and do a chi-square fit, okay, typically it is to be done in MT. I'm not showing it because the Higgs has been discovered. Now there is to be something called the famous blue plot. Okay, where the blue was the region which was excluded actually. Okay? And if you do a chi-square, in image plane. So chi-square between theory observables and experimental observables. And you ask what is the mass of the Higgs boson, which fits the data very, very well. Because it's a free parameter, and you run the top mass as a free parameter up to the experimental range. It comes out to be around 80. But the main reason why this was not so taken seriously because in all this process, the Higgs enters through logarithmic divergences. Okay? So if you want a correction to the sin square theta W, the sin square theta W, delta sin square theta W coming through the Higgs will be proportional to log mh square by some e square. Okay, so it's very sensitive because log it can take a large number and still make it a small thing. So you cannot pinpoint precisely what the number of the Higgs mass is. But so they gave a range of say 60 to 135 later on, but earlier they should be up to 200. So electronic precision test always preferred a very, very light Higgs. They always preferred a very, very light. So answer this question. So they wanted a very, very bright. This was, if you are a bit more aggressive, you want to put in low energy data, 135. So electronic precision test always wanted a very, very light Higgs, and the search for the Higgs continued after the Z pole results. After the Z pole, the root S started increasing up to 11. So they started increasing the root S. So they brought it all the way up to 2 times G. Root S is equal to 2 times G. So then they claimed that they found 2 events of Higgs like 150 G. At 150 G, they found 2 events. But it was finally, that was asking for explanation sort of thing. So people said, you found these 2 events because you are asking for explanation of that. But anyway, it was closed down and LHC was doing actually. So, yeah. Okay.
So, for the new MW calculations,
New MW.
Yeah, so that's how they are predicting the mass of Prof and this calculation the mass of
The new MW controversy,
Yeah.
80.3 to 80.41.
Yeah,
So that requires, okay, they are doing the same thing. The point is, this electronic precision test, you want to somehow violate it. So that requires new contributions to MW. Okay. So typically, they require a new vector boson, which can mix, which has a hypercharge 1 or something. That was the influence we had. I have put a hypercharge 1 the other day. Okay. So you need some 131 or something, a hypercharge of very with a hypercharge 1, a triplet boson or something like particle, which can mix with the W, so that there is a small shift in the W. So you need some extra mixing. But nobody believes that result. I don't believe that result. I don't trust this CDF result. So, okay, for people who don't know, this electronic precision test is still in the game, actually. So, even now, you think that 90s it is done, no, it's not yet done, actually. So, the electron, so right now, the error bar on MW, the mass of MW is around 8.3 plus minus is around 15 MeV. Okay. So you want delta MW is around 15 MeV, and the maximum LHC will bring it down to 12 MeV in a few years' time. But the recent CDF has claimed that they changed the center values from 8.3, they changed to 8.41 GeV, and the error bars are very, very small. 0.5 or 0.6 millimeter. Okay, very small millimeter. So they claim that they are much more precise than the future LHC results. Okay, okay, and they have different analysis method and everything. CDF is an experiment which has closed down long ago, some 10 years ago. But they realized data and they claim that they have now a new settle value with extremely small error bar. The error bars, you should see the paper, I don't remember now, it's much smaller than 10 mm, 8, 7 or 6 per millimeter, it's very small. How much? 9 mm, yeah. It's smaller than this, definitely. It's around 9 mm. It's just unbelievable actually. Okay. I don't know how they got that number. Yeah, it's controversial, let me not influence your minds. You can write papers on it. It is called, you guys should write papers on it, but yeah, get some citations in it. Okay. So, this is about the gauge symmetries. So, the gauge symmetry corrections, they are extremely sensitive to the experimental numbers. If you want to modify a little bit of the gauge symmetry part of the standard model, you are going to run into problems with the experiment. Because the experts measured it so well. Okay. So let me now come to fermion masses corrections, and then I will stop. Yeah. And because the Higgs will take some time. All the fermions in the standard model are protected by something called the chiral symmetries. What is a chiral symmetry? Chiral symmetry is nothing but some Q of theta is equal to P of theta. It's a global symmetry. So this is some chiral symmetry. So fermion masses, meaning these corrections are protected by chiral symmetries. So what it means at loop level is that any correction to any fermion mass, say for example electron mass, is always proportional to itself times some log and something loop function. Okay. So any fermion, so you can generalize it to any fermion. So there is no large correction. There is no large correction, no large one loop correction to the fermion masses. So it's always proportional to itself, so it will be very small also. Say for example, if you want any correction to fermion mass, so there could be diagrams of this type. And so on. So you can resum them like what you do in QED. Okay? You can resum them, but there are more diagrams and more W's and everything. And then you can actually calculate the Prof later, but it will always be proportional to the mass of the fermion mass. So sigma f, which we typically calculate for the self energy of the fermions, will be proportional to the standard model because of this protection of the chiral symmetries. So what does it imply? In the limit MF is equal to 0, you have a new symmetry with A, which is the chiral symmetry. Okay. In the limit MF is equal to 0, this symmetry is exact. So every correction to the fermion mass will be proportional to, in other words, its mass. So typically it is expressed in terms of a cross. Okay. Every correction to the fermion mass will be proportional in the self-energy diagrams will be proportional to the fermion mass itself. So this is because fermion masses are chiral in nature. Fermion masses in standard model are coming from psi L bar psi R terms. It's not purely psi L or purely psi R. So that means we need to have, if you write in terms of chiral Feynman rules, okay? If this is left chirality, this will be right chirality. always. So it will always, you have to insert a mass term so that the correction is always proportional. So
What was the last one? So,
the correction is always proportional to this cross. So you can put this cross anywhere. Actually, in the standard model, this cross will appears externally. So always appears externally without the gauge positions. It can appear internally only with the things. Okay. So this is not the charge line. No? By the way, this is the parallel line. This arrow is the parallel line. This left, there is right. This is sometimes what we use for the matter. Okay. So at the one loop level, this part of the diagram we have seen that it is always protected by some symmetries. Okay. And so the corrections are not very large. So these are well measured, you know, all the masses and everything. So they are protected by under quantum level. Okay. Okay. I'll stop here. These two, I wanted to do these two hours today, but I didn't finish it. So I'll do in the next class. I didn't realize it's not going to go. So any questions?
If the correction is of the order of mass, then correction is actually big. But
No, it will be not big, no?
like
But yeah,
delta f is the order of mf. So,
yeah. It's always proportional to this.
so the
Yeah.
correction is
It cannot
big.
be large. It's not. It cannot be arbitrarily large. No, it's not an infinity or something which is coming in. Yeah, it's,
But it is controlled by the mass.
Pardon?
Now it is controlled by the mass of that particular.
Exactly. So there is some symmetry in the limit. This mf goes to 0. This correction also goes to 0.
But only if mf goes to 0. Like,
Of course, that's an important point. Right? In the limit mf goes to 0, there is a new symmetry in the theory.
which is the correction.
So yeah, chiral symmetry. Now, any corrections to this will break that symmetry. Any corrections to the fermion mass will always break that symmetry, and that symmetry breaking is only by the mf term. So that's the reason why you will have at any order in perturbation theory, it will be mf square by 16 pi square.
So maximum it could have been order of mf.
Yeah, it will always reduce. It will be convergence in this one. So this is actually what yf square by 16 pi square. Okay, I type some web or something, whatever it is, essentially. Okay, and so on, so on, so on. So this will always be small and protected. So there is no unknown parameter in this. So there is no gauge. There will be a gauge correction actually, but it will be very small. But it will be proportional always to mf because of the chiral nature. Even this part has a gauge coupling. Okay, the total thing will always be proportional to y or Ka coupling or the fermion mass itself.
But in your theory, if there is another particle like X, which can mix this left and right, and that coupling is not
It's possible. Suppose if you have multiple Higgs, okay, it happens in supersymmetry. So we can, but in most cases, chiral symmetries are always present, even in supersymmetry cases. But you can have these chiral flips inside loops in supersymmetry because you have extra scalars, a lot of scalars coming in. So you can have chiral flips into the in the scalar counterparts of fermions. So you have, if you have new vectors in your theory, there is a problem, which are non-chiral in nature. So if you have some new interactions or something which are non-chiral in nature, then it's a problem. But still, you have to equate it to the mass at the end of the day. You have to generate a mass, so it will be proportional to the mass times something else. So if we have a theory which is left-right symmetry, if you have vectorial masses, bare mass terms, okay, or if you have vector-like particles which are non-chiral, meaning both left and right are charged under electromic symmetry. So SU2. Those kind of things can be large connections because they are bare masses. So they are bare parameters in your theory. And if there is a connection to the Higgs, we phenomenologically arrange them that they are very small and everything. But if you have extra particles and everything, and if they are very light with these masses, they can go very large. Better fermion masses can go very large if they have large couplings with the Higgs. Anything with a bare mass proton. Because because it's generated spontaneously symmetry within, so you don't have this problem. Okay, yeah, I'll do these two. This is also this is so slightly more, and then I'll come to this. It's a bigger issue also for DSM models, and then all this I summarize so that what are the reasons why we want to go with DSM. Okay. Yeah. Any further questions? Yeah, Tuesday is a holiday. Okay. I may or I may not come. No, I send an email to all of you. Just send me an email with all your names so that I will be able to. Or I'll put a message in the Teams. That's easier. Okay, don't worry about it. Don't send me. Please don't send me. I'll just put a message on the Teams page. Okay. Tuesday, I don't know. It's a holiday. I don't want to bother you guys. We have to find somebody to